In Wbut curriculum, you have physics as one of your paper, and for first year, first sem, the paper code for physics is BS-PH-101, and this paper is for 3 departments, that is civil, mechanical and CSE. The same paper is for the second semester. The paper code is BS-PH-201, and this paper is for 2 departments, that is EC and EEE. Now this entire physics syllabus is classified into 5 modules. Statistical mechanics is one of the modules, and that is module 5. So I will teach statistical mechanics. Now this entire module is classified into 6 lectures. First lecture deals with comparative study between Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac statistics. In second lecture, I will show you numericals from Macrostate and Microstrip. In the third lecture, we will discuss the basic concept of ensemble and phase space. Fourth lecture will comprise of a very important graph that is called the Fermi-Dirac distribution curve at temperature 0 Kelvin and temperature greater than 0 Kelvin. Fifth lecture, that's the derivation, a mathematical relation between average energy and Fermi energy. And the last lecture, that is lecture 6, we will derive Planck's law from Bose-Einstein statistics. So please follow lecture 1 to 6, and the references are there on your screen. So now we come to lecture 2, and for lecture 2 we have the topic Macrostate and Microstrip. In lecture 1 we have covered the difference between the 3 statistics: Maxwell-Boltzmann statistics, Bose-Einstein statistics and Fermi-Dirac statistics. So now in this lecture we are going to discuss about 2 important concepts from statistical mechanics. One is macrostate, the other is microstate. For macrostate, it says that in a system or a container you have large number of particles, and so these particles will have different energy levels, and the particle is occupying a fixed volume. So when you have the number of particles enclosed in a container having fixed volume and fixed number of energies where the particles will be distributed in a fixed volume of the container, then that quantity or that information is called macrostate. For example, here you have, if you consider a container containing many particles, and if you distribute these particles into energy levels, and let us say that out of this 3 particles lie in energy level E1, 2 particles in energy level E2, and 1 particle in energy level E3 and 1 in E4. So you have total number of particles that is fixed, total number of energy levels fixed in a given enclosed in a container having a volume V. So this information is called microstate. Now what is microstate? Microstate states that for that given information of macrostate, that means from macrostate, suppose if you have a certain number of particles lying in energy level E1, E2, E3, E4, and then you want to distribute these particles, that means place these particles in different energy levels. So how many ways you can place these particles in these energy levels? So here in this case you have 3, 2, 1, 1, and you can also distribute in the other way, like in the energy level, in out of these 4 energy levels you can also distribute from 2, 3, 1, 1. So when you distribute these particles in different meaningful ways, so this number of ways is called microstate. Now we take a example, a numerical, which is from Wbut question paper, that Find out the number of possible arrangement of two particles in three cells for Maxwell's-Boltzmann statistics. So when you have two particles and three cells, and you have to calculate the number of possible arrangements, that means the number of ways or number of microstates. So in this case, when you are dealing with Maxwell's-Boltzmann statistics, as we have done in the lecture 1, that Maxwell's-Boltzmann statistics deals with distinguishable particles. So the two particles that we have it in the problem, I name them as A and B. So the first particle A and the second particle is B. Why they are named different? Because they are distinguishable. You have to distinguish these particles. Now I have three cells or three quantum states or three energy levels, you can say. Let us say the first energy level is E1, E2 and E3. So you have three cells and you have two particles. Now how will you arrange these particles, or number of ways you can arrange these particles? Then this information or the number of ways will give you the number of microstates. So here in this case, when I talk about macrostate, it says that if you ask me from this problem what is the meaning of macrostate from this numerical, I would say that for macrostate it means that you have three cells or three energy levels and you have two particles. Now when these two particles to be arranged out of these three energy levels or three cells, then these possible arrangements are called microstates. So let us see how these two particles can be arranged in three energy levels. In the first case, I can make the two particles A and B sit in energy level E1 or cell E1. The other two cells remain vacant. So this cross sign means that there is no particle. In the second case, I can say that energy level E2 or cell E2 is filled with two particles A and B, E1 and E3 is left behind. Similarly, I can place A, B, the two particles in the third energy level, the third cell, keeping the first and the second blank. In this way, I can also make A and B separate. They can sit in the cells separately or alone. So A can sit here in the energy level E1, B can sit in energy level E2, and C remains, or energy level E3 remains blank or empty or vacant. Similarly, I can interchange their position. So B comes here, A in E2, E3 remains blank. Like this way I can make A blank B, B blank A, blank A B, blank B A. So there are no other possibilities in which I can arrange. So there are 9 possibilities or 9 ways I can make these two particles sit in three cells if the particles are Maxwell's-Boltzmann. Now the point to remember is that, as we mentioned in lecture 1, that these two particles are distinguishable, and the second point was that these particles will not follow Pauli's exclusion principle. This is very important. When the particles do not follow Pauli's exclusion principle, which means that these two particles can stay together in a cell or they can sit separate, they can sit individual. So when Pauli's exclusion principle is not followed, that means you can make the arrangements making the particles sit together or making the particle sit alone. So you have in this problem, you have 9 ways. So 9 is called the number of possible arrangements or 9 microstates. I can also calculate this number 9 or number 9 microstates from a given formula, g to the power of n. What does g signify here? G means the number of quantum states. In this problem, the 3 cells here, or the 3 energy levels, resembling the number of quantum state. So g here becomes 3. And how many particles? We consider 2 particles, so n becomes 2. So if you substitute the value of g and n, so you get 3 square, that gives you 9. So you can make this table, or you can recheck this with this formula, number of microstates, and you get the same 9 ways or 9 micro. The same number of particles and same number of cells, but the statistics here now is Bose-Einstein statistics. Now in Bose-Einstein statistics, you have two particles. In the given problem, you have two particles. So because Bose-Einstein statistics is indistinguishable particles, so we name it as AA. In the previous case, for Maxwell-Boltzmann statistics, we considered AB. In this case, because it is indistinguishable, it is AA. And the second point is that Bose-Einstein particles do not follow Pauli's exclusion principle, which means that these two particles in a given cell can stay together or they can stay individual. So following these two properties or two rules, if we try to place these particles in the given cells, and we have three cells E1, E2, E3 in the given problem, two particles. So now these two particles can stay together or they can stay alone. So let us start distributing. In the first case, we can write down that the two particles are in cell E1, E2 and E3 remain blank. Similarly, I can make AA, the two particles in cell E2, E1 and E3 remains blank. Following the same, I make E1 and E2 blank and put the two particles in E3. So because it doesn't follow Pauli's exclusion principle, which means they can stay even individual. So I can place this single particle A and another particle A at E1 and E2, and E3 remains blank. So there is another two possibility, that is blank AA and A blank A. So while distributing, you have 6 such possibilities. So we can say that there are 6 possible arrangements, or we can say that total number of microstates for this case is 6. Now if you want to calculate this number of microstates 6 using theory, you can use this formula: W is equal to n plus g minus 1 factorial divided by n factorial g minus 1 factorial. In this problem, n means total number of particles, here it is 2, and g means the number of quantum state, here it is 3 cells. So if you substitute the value of n and g here in this formula, after calculation you are going to get 6 microstate as we have shown in the tabulation. So now similarly we take the same problem, but now we are going to solve it in FD statistics. So find out the number of possible arrangement of two particles in 3 cells for FD statistics. Now FD statistics, if you just recall the slide 1 from lecture 1, then you have the table, the difference table. The difference table suggests that for Fermi statistics, the particles are indistinguishable. So again, the two particles are named as AA. And now the particles, in the second point, the particles followed Pauli's exclusion principle. When I say particle follows Pauli's exclusion principle, it means that these two particles, they are not going to stay together in a cell or in an energy level. They have to stay individual. So following this two rule, I can substitute as AA blank, blank AA, A blank A. So because this, like the previous case, Bose-Einstein statistics, you had the two particles staying in a given cell, but for FD statistics, you have to put them as individual. So how many possible arrangements you have? You have 3 possible arrangements. So we can say 3 microstates. Like the previous cases, I can also use a theory to calculate the number of microstates. Here the formula is g factorial divided by n factorial g minus n factorial. In this case, g means number of quantum state, here it is 3 cells. N means number of particles. So if you substitute the value of g and n as 3 and 2 respectively, g is 3 and number of particles is 2, you get 3 as your answer. As also in the distribution table you have thermodynamic probability mean. It means that for a given macrostate, and this is applicable for distinguishable particles, that means for Maxwell-Boltzmann statistics. So when you have a given macrostate, so your macrostate information is fixed. Okay, so you have the number of particles, you have the number of energy levels, and now you have the fixed number of that how many particles will lie in which levels. So when this is fixed, you can define or you can calculate the number of microstates from the theory of thermodynamic probability. So what does the theory says? W is the thermodynamic probability, capital N factorial by N1 factorial, N2 factorial dot 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 Ni factorial. What does this mean? N means the total number of particles. In this example, you have 4 energy levels where in the first energy level you have 3 particles, in the second you have 2 particles, in the third and the fourth you have 1 particles each. So if you say what is N1, I would say that number N1 stands for number of particles in the first energy level. So how many particles in the first energy level? 3. So N1 becomes 3 here. Similarly, E2. So number of particles in the energy level E2 is N2. So N2 becomes 2. Similarly, number of particles in energy level E3 is called N3. So N3 becomes 1. And similarly N4, that is number of particles in the fourth energy level, that is N4 equal to 1. And what is then the total number of particles? 3 plus 2 plus 1 plus 1. That gives you 7. So 7 factorial divided by the number of particles in each level, and if you use the factorial formula here, you get the number of microstate, which means that if you give the definition that your 3 particles should be here, 2, 1, 1, if you keep this definition fixed, so that is macrostate, that how many particles in which levels, if that is fixed, then the particles like A, B, C, D, these particles may different in different occasion they can change the number of energy levels or the place value of energy levels, but the number of particles in the energy levels are fixed. So that is macrostate. Macrostate basically gives you that how many particles in which energy level, right? But when you change these particles, if you ask me how will you change, if you have a distinguishable particles, these particles will be A, B, C, D, E, F. So they are different particles. Each particle is different from the other. So these particles, keeping the phase value, keeping the macrostate definition fixed, that is how many particles to be placed in which energy level, the different particles and their arrangement, keeping the macrostate definition fixed, is called thermodynamic probability. So I repeat, for a given macrostate, for a fixed macrostate, if you change the number of ways these particles, this number of ways will give you microstates, and that is called thermodynamic probability. Let us do a numerical. This is from Wbut question paper. So what does the numerical say? That 4 distinguishable particles for the macrostate 3, 1, and the number of possible arrangement you have to calculate. So number of possible arrangement, when they say, it is actually the number of microstates. So for this macrostate 3, 1, you have to calculate the number of microstates. So basically you are actually calculating the thermodynamic probability. So because it is written, see, distinguishable particles, so particles straightway does not mention that whether the particles follow MB, B and FD. They are saying that the particles are distinguishable. So straightway you have to connect that these particles follow Maxwell's-Boltzmann statistics. So they are MB. How many particles? 4 particles. So because they are distinguishable particles, I have to name them as A, B, C, D, because they are distinguishable. You can distinguish between them. Now what do you mean by 3, 1? It means that you have 2 cells or 2 energy levels, okay, and in the first energy level you have to keep 3 particles, and in the second energy level you have to keep 1 particle. So that is fixed. This definition of macrostate is fixed. So when they are saying macrostate 3, 1, it means that they are not saying that how many energy levels or how many cells. This bracket term gives you an idea that basically you have 2 cells or 2 energy levels. In the first energy level you have 3 particles. You cannot change this. The number of particles in the first energy level to be fixed, and the number of particles in the second energy level to be fixed, that should be 1. So this definition will not change. So what will change? The name of the particle itself. So there are 4 different particles and you can make different arrangements, but keeping this in mind that the 3 particles should be in the first and 1 particle in the second energy level. So if you try to make an arrangement, so your first case will be ABC will be here, E2 in the second energy level you can place D, B, C, D you can place A in the E2 level or E2 cell, A, C, D you can place B in the second energy level, A, B, D all together in the energy level E1, C separate to E2. So how many possible ways you can make? You find 4 ways, 4 different ways. So you can say thermodynamic probability is equal to 4 or number of microstates is equal to 4. But if anyone asks you how will you calculate this from the theory, you can just place total number of particles. How many are there? 4. So factorial 4 divided by how many particles in the first energy level? 3. So factorial 3. How many particles in the second energy level? 2. So 1. So factorial 1. So if you place 4 factorial by factorial 3 into factorial 1, you after calculation you will get 4 ways or 4 microstates of thermodynamic probability is equal to 4. So now we have covered macrostate and microstate in this lecture. Now what type of theory questions Wbut in this question paper they ask? So they ask you define macrostate and microstate. They also define they may ask you to define what do you mean by thermodynamic probability. So this has been discussed and this is a straightaway question. So now we come to the end of lecture 2 and we covered macrostate, microstate, and thank you again for your attention.